Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered how our brains figure out new puzzles, especially when it is tricky and physical? What if the way you explored could actually make you smarter? Today, we're diving into some fascinating research that explores exactly that. Think about trying to open a really complicated lock or a tricky puzzle box. How do you even start? Do you just randomly twist things? Or is there a smarter way? Scientists have been trying to figure this out, and they've come up with a super cool new puzzle just for this. So scientists are really interested in human exploration. It is how we learn and solve new problems. But a lot of the old ways to study this were a bit too simple. Imagine learning to tie your shoes by only seeing a drawing, no actual shoes involved. That's kind of what some studies were like. They simplified things so much that it didn't really feel like real life anymore. Humans evolved to solve problems in the real world with all its messiness and physical stuff. That's the big question these researchers wanted to answer. How do we use what we've learned before to tackle totally new problems? And importantly, can we use this knowledge to build smarter robots or AI that can learn like we do? They realized we need to study exploration in environments that are more like the real world, where we have to actually do things, touch them, and figure them out. To do this, they created something called the lockbox paradigm. Imagine a puzzle box, but instead of keys and tumblers, it has sliders. You have to move these sliders to unlock it. The tricky part is you don't know which slider does what or what order you need to move them in at first. It's like a mechanical enigma. The game looks different each time, with sliders in different places, but the hidden rules underneath are always the same. This forces you to actively poke and prod to explore rather than just guessing. This hidden mechanism is key. It means you can't just look at the lockbox and figure it out. You have to physically interact with it, move the sliders, and observe what happens. This is where the real learning happens, through trial and error and carefully watching the feedback. Now, here is where it gets even cooler. To make this feel like real-world interaction, they used a special device called a haptic device. Think of it like a fancy joystick that lets you not only control things on screen, but also feel resistance and texture, like you are actually touching and pushing the virtual sliders. This is a big deal because researchers believe that our real-world problem, solving skills, are deeply tied to our physical senses and movements. So, how did they run the experiment? They had 91 people play with these lockboxes. Each person got a slightly different version of the puzzle, some easier, some harder, based on how many hidden rules there were. They played for about an hour. During this time, every time someone tried to move a slider, the researchers were watching and recording everything. To motivate participants and add a cost element, they started with 1,000 points. Every single time they interacted with the slider, whether it worked or not, they lost 10 points. The game ended when they unlocked the lockbox or when their points ran out. This introduces a kind of cost to their exploration. Every move cost them something. And what did they measure? One important thing was when and how often people tried to move the actual target slider, the one that would unlock the box. They figured people would only try it when they felt pretty confident they had figured out the right steps. Another key measurement was something called state revisits. This means going back to a slider setup or configuration that you've already tried and found didn't work. If you keep going back to dead ends, it means you aren't exploring very efficiently. They calculated a state revisit rate, and the lower rate meant people were paying more attention and exploring smarter. They also looked at the randomness of the moves. Were people just randomly poking around, or were they developing a systematic pattern? Over time, as people learned, they expected the moves to become less random and more strategic. So, what did they find? The first big takeaway is that people naturally move from exploring everything to exploiting what they've learned. Initially, people might try the target slider a lot, hoping for a lucky break. But as they play more and learn the rules, they try the target slider less often. This is because they're becoming more strategic, only trying it when they're sure it will work. And that randomness, it goes way down as people play more. At first, it's like a chaotic search party. But as they gain knowledge, their moves become more deliberate, more focused. This is the shift from exploration to exploitation, trying out new things versus using what you know to get the job done. Another big principle they uncovered is cost minimization. People naturally try to take the path of least resistance, or at least the path that seems to lead to the quickest solution. When a slider didn't work, they tended to just try the sliders right next to it. It's like saying, okay, this didn't work, let me try the closest one. It is less effort and may be connected. But if moving a slider did work, guess what they did? They immediately tried the target slider. This shows they're looking for the quickest win. Even if moving a distant slider took more physical effort, they were willing to do it if it was the most direct route to unlocking the box. They're always trying to minimize the total effort or cost to solve the puzzle. Scroll attentiveness drives efficiency in exploration. Figure 5a illustrates the connection between state revisits and learning efficiency. Browse now, let's talk about attentiveness and how much it matters. Remember those state revisits going back to old failing configurations. The study found that people who revisited fewer old states, meaning they were more attentive, were also much better at learning the lockbox rules and solving it faster. Scroll figure 5b reveals two key trends. First, there is a complexity effect, such that more complex lockboxes indicated by higher lines tend to have higher state revisit rates. Browse, they also saw that harder lockboxes, the ones with more hidden rules, naturally led to more revisits initially. That makes sense, it is more confusing. Scroll second, there is a learning effect, such that regardless of complexity, the revisit rate decreases across trials as participants develop more efficient exploration strategies, with increasing experience. Browse, but importantly, even with those harder puzzles, people got better over time. The revisit rate went down as they learned. This shows that even when things are complex, focus and experience lead to more efficient exploration. Scroll physical interaction alters learning. Participants who used the haptic device completed the lockbox in fewer steps and converged faster on more efficient strategies compared to those who used the mouse. Fig. 6a browse and here's a mind-blowing finding. They compared people using the haptic device to people using a regular computer mouse. Guess who did better? The people using the haptic device, they solved the lockbox in fewer steps and learned faster. This suggests that feeling the physical resistance and feedback of moving things makes a big difference in how efficiently we learn and explore. Scroll furthermore, figure 6b shows that participants who used the mouse revisited previously explored states at a higher rate compared to those who used the haptic device. Browse, not only that, but the mouse users revisited those failed states more often. It's like the physical connection, the greater effort and feedback from the haptic device made people more mindful, more focused, and less likely to wander back into unproductive paths. The physical cost, the effort of moving the haptic device, seemed to sharpen their attention and improve their learning. Scroll conclusion. Our study introduces the lockbox, a complex and ecologically valid paradigm designed to deepen our understanding of human exploration strategies during problem solving. So Browse, what does all this mean? This lockbox puzzle is a really smart way to study how we explore and learn in ways that mirror the real world. Scroll, these findings motivate research on transferring these dynamics into robotic systems to potentially improve their learning efficiency and robustness in real-world tasks. Browse, the big takeaway is that our exploration isn't random. It is guided by principles like cost minimization, trying to get the most bang for our buck, or in this case, the most progress for the least effort. Our attentiveness is crucial for efficient learning. And surprisingly, physical interaction seems to boost that attentiveness and learning efficiency significantly. This has huge implications for fields like robotics and AI. If we can design AI or robots that learn with more physical engagement, they might become much better at tackling complex, real-world problems. Scroll in the future. Collecting more data using an extended lockbox paradigm that allows for adjustable levels of physical demand and other cost factors, such as time, will further illuminate the impact of these elements on exploration in problem solving. Browse now, no study is perfect. The researchers mentioned that they could investigate this even further. They want to explore how different kinds of costs, like time pressure versus physical effort, affect our exploration. They also excluded some data because some puzzles were too easy and some were too hard, which is pretty common in research. But the core findings are strong. We're not just passively observing the world to learn. We are actively exploring it, and that physical interaction is a powerful tool for figuring things out. It's pretty amazing to think that the effort of physically pushing and feeling something might actually make us better at solving problems. It highlights how our bodies and minds work together in ways we're still discovering. This research gives us a deeper appreciation for the complex, often subconscious strategies we use every single day to navigate and understand our world. What do you think about these findings? Have you ever had an experience where a physical task helped you understand something better? Let me know in the comments below. If you enjoyed this dive into human exploration, please give this video a thumbs up, subscribe to RUBIN'S Mind Lab for more fascinating research breakdowns, and hit that notification bell so you don't miss our next episode. Thanks for watching, and I'll see you in the next one.